Thanks, Diego. And if anyone has any questions, please post it on the Q&A. And thanks. I think I like your last quote, Diego. 3G brought the gig economy and 5G brings the gigabyte economy. That's great. Thank you.
You can use that.
Yeah. Next, I would like to invite Madhukar, Dr. Madhukar Budagavi. He's a senior director at R&D in Samsung's Innovation Lab, and his team works on the next generation immersive media processing, compression, and delivery of for 5G and its standardization. And he's also a co-editor of the Springer book on high efficiency video coding, algorithms and architecture, which was published in 2014. And Dr. Budagavi has co-authored 40 plus book chapters, technical papers, and he has a lot of patents, 90 plus granted patents related to multimedia compression, processing, and video streaming. He will talk about different media types, such as volumetric video enabled by 5G, associated challenges and opportunities for innovation. Madhukar, please.
Thanks, Naresh. Let me just share my screen. Okay, so I hope everybody can see the screen. So today, I'll be talking our thoughts on, what next-gen multimedia for 5G and beyond would be. This is a constant question that gets asked and got asked today also in the panel, what will be the killer application for 5G and beyond? 5G is getting deployed, so good. But what would be the killer application? So like Diego mentioned, XR is one such application. Will we have like truly immersive extended reality as shown in movies? That's one option. Second option is, high fidelity mobile holograms. There are many startups, many big companies working on technologies right from capture all the way to devices, which can provide this kind of a hologram type of an experience. But they're all in the prototype stage now. Third one is multi-angle live sports. Here you have a stadium which is covered by many cameras, so users can pick and choose whatever angle they want to see. Other potential killer applications, with the era of Zoom and COVID, there is this thing called Zoom fatigue, where the eyes get tired if you watch a 2D screen for a long time. So are we going to get some new type of displays, volumetric displays that will provide, truly immersive telepresence, personalized esports, and so on. So the key thing behind all of this is there is a paradigm shift that is happening. We are in the era of traditional 2D video. We are moving to volumetric video in many different ways. And 5G is one of the things that is making this happen, because as you will see in my subsequent slides, the amount of data generated by volumetric video is an order of magnitude more than 2D video. So with 5G coming in, all these things become feasible. Of course, you need innovations in the whole ecosystem, including, capture, distribution, compression, and so on. So one more thing which is important is, I said, the amount of data that is generated is huge, but at the same time, the compute complexity that is needed for this is also huge. So we will look into, I have a slide on it, on split computing, wherein a lot of the processing could be offloaded on edge or any other compute network, compute node, basically on the network. So what is the volumetric video? So what I'm presenting here is at a very high level, and we can get into the details during Q&A if needed. So volumetric video compared to 2D video captures basically the whole 3D space, not just one snapshot of a 2D space or an object. So, the viewer can interact with it. So I underlined interactivity because that's important. With 2D, the amount of interactivity you can have is limited. So the user can interact with basically the volumetric video, and he can view the video image from any viewpoint that he wants. So the terminologies that are typically used, are, point clouds, light field, multi-view, multi-angle videos, 6 DOF, 6 degrees of freedom, hologram, and so on. So on the left side here, what you're seeing basically is a point cloud. So if it were just a traditional 2D, you would just take a snapshot. Whereas to capture the point cloud, and this was captured in Samsung in Plano, what you will have is, you'll have around 80 or 100 cameras that are focused on the person, and they're capturing basically the same person from many different views, and then you do a 3D reconstruction. So the person here is actually a set of points, and we call it as a point cloud. The second one is multi-view, multi-angle. I briefly alluded to it. Here you have multiple cameras in the stadium, so of course you can view it from any particular direction that you want. But in addition, you can have, what is called as 4D replay, wherein if there is a particular particular important, like for example, uh, a person has thrown, the baseball. Sorry, I don't know the baseball terminologies, but sliding here. So what you can do is look at it from at a stage wherein you have to freeze a scene and you have to look at it. You just cannot basically turn around and rotate the scene and look at it, look at the video, and that requires an order of magnitude more bandwidth. So 5G will basically enable that. The other one is basically light field. So here, these things have been around for a long time. I think the key thing is, now is the time where, these things are becoming possible. So here also, you're capturing the person from many different angles. And this particular video consists of around 15 views. So these 15 views, of course, you can see it on a 2D display, and this is the kind of effect you will get. But if you feed this into a volumetric display, then, without glasses, you're able to look at the person from any particular angle that you want. So these are, some of the new multimedia, new formats that are coming in. Now, what are the technical challenges? Of course, like I mentioned, the capture complexity is very high. The bandwidth requirements are also very high. The latency requirements for interactivity, you need ultra low latency of the order of 20 milliseconds. So the numbers we are putting here, are just an estimate. So please take it with a pinch of salt. So complexity around 60x. The raw data rate, this is before compression, is around 100 gigabits per second. The latency requirement, from 200 milliseconds goes down to 20 milliseconds. Now this is new content, so you'll need to generate new content either from existing content or with new cameras and new modalities. A camera, I mentioned, it can be 80 cameras, or it could be just be a single RGB camera and a depth camera on your mobile phone. But to really get the whole wow effect, a new generation of devices are needed, which can display volumetric contents, and companies are working on it. Then, of course, you need efficient compression techniques. MPEG has been standardizing, MPEG-I standards. So there are many different standards for point cloud compressions. There is one activity called immersive video, which is looking at light field video. So, they give around, 100 to 200x compression. So which is good. Of course, more is needed, and, MPEG is continuing to work on it. The last one, like I mentioned, you do need mobile edge computing to offload some of the complexity, either in the capture side or even on the rendering side. So let me just briefly talk about it, split computing. So future applications utilizing volumetric video require extensive computing, not only because the number of views are more, but also, some of the formats such as point clouds, a point cloud can have around 1 million points, and you need to render it. So that requires a lot of computational complexity compared to just a plain 2D video. So the what will basically help is split computing. So what is split computing? It makes use of resources on the network. Either the compute power might be basically in the base stations or in the MEC servers. So this, is showing at a very high level a particular example. So if it's a standalone device, like an AR glass, the compute power it has is low. So you might be able to render the volumetric content at a very low resolution, so you get blurred quality. Whereas if you're able to offload the compute onto basically a base station or an MEC, then you can render the volumetric content not on your device, but basically on your compute node. And then Once the rendering is done, then you can take a snapshot of that and send back the 2D video to get good quality. So this is one of the things that we have been working with UCSD, Sushi as well as Sujit, where they have been looking at split rendering. It's an example of split computing. Split computing means any compute load could be offloaded. Split rendering, we are offloading only the rendering part. For split computing to work, due to the latencies involved between base station as well as the compute device, as well as your AR device, what you will need is some type of viewpoint prediction. So you would need to predict where the user is going to look at, share that information to the base station, so it can do some look ahead prediction and then generate basically the render view into the future. So there is a reference here that you can look at. So that's some research along that particular direction. Not only do you need rendering technology, but you need other technology which can predict where the user is going to look at. So to conclude, volumetric video provides highly immersive experience. Several technical challenges remain. You need new format, compression, content generation, devices, distribution. I put everything here. So my intention here is not to scare people that this technology is not ready. There are some parts of it which are ready and which are being deployed, and some parts which require time for basically deployment. But there are a lot of open problems that can be addressed to basically accelerate the transition to volumetric video. So with the advent of 5G and its super wide bandwidth, volumetric video applications become feasible. So that's, I think, one of the key things. The bandwidth requirements are high. So our belief is volumetric video will lead to fundamental new media services on phones, TVs, and future devices such as AR glasses, volumetric displays, and so on. Okay, thank you.
Thank you, Madhukar.